Okay, so I've started the recording. So we are going over the homework from homework 5. And so we are looking at number 3 from 4.5.5.4. So I put it here on Word. So the question is, a random sampling of 4 members of a 150 member club has shown that 3 prefer no smoking in the clubhouse dining room. What is the probability that this will occur if in fact only 20% of members prefer no smoking in the dining room? Find this probability assuming that the sample was obtained under each of the following. So A, sampling without replacement, and B, sampling with replacement. So do you want A and B? Okay, so let's see.
Yeah, I just didn't really know what they meant by A, by sampling without replacement.
Okay, so sampling without replacement would mean that when they choose a member, they don't then replace the member. Okay, so okay, so it's 4 members of a 150 member club has shown that. So find this probability. So find the probability that so the question is, find the probability that a random sampling of 4 members of a 150 member club has 3 no smokers, or 3 prefer no smoking. So I'm abbreviating it like that. Okay, so we want to find this probability. Okay, so let capital A equal that event, equal the event of 3 out of 4 chosen in a 150 member club prefer no smoking. Okay, so we want to find the probability of A. So that's equal to n sub A over n. Okay, so the denominator is the number of ways to choose. So this is without replacement. So you're not replacing the members each time. So I'm just going to get the notation for it. You can hear me. Okay, good. So you have 150 members in your club, and you want to have a sample of 4 of them. So 150 choose 4 is the denominator. It's a number of ways of choosing, having a sample size of 4 people from that 150 member club. The numerator is going to be the number of them, of those 4-person samples, in which exactly 3 of them prefer no smoking. So to do that, copy this. So in order to have exactly 3 that prefer no smoking, 20% of the members prefer no smoking, right? So notes, 20% of 150 prefer no smoking. So what that equals, 20% of 150 is 30. So 30 prefer no smoking. Okay, it's just 0.20 times 150. That's 1/5 of 150, which is 30. So 30 prefer no smoking. So that means that 80%, since 20% prefer no smoking, 80% of 150 prefer smoking allowed. Okay, and so then that's just the rest of it. So that would be 120, right? Because 30 plus 120 is 150. So 120 prefers smoking allowed. So I'm abbreviating it. Okay, so what we want are exactly 3 members who prefer no smoking. Okay, so we want exactly 3 that prefer no smoking. So we have a total of 30 that prefer no smoking. We want to choose 3 of those people, 3 out of 30. So it's 30 choose 3. Then you multiply that by, you have 120 that prefer smoking, and you want 1 of them who prefer smoking, right? If you have a total of 4 people and 3 of them prefer no smoking, that means the other 1 person prefers smoking allowed. So it's 30 choose 3 times 120 choose 1 divided by 150 choose 4. N sub A is the number of ways. N sub A is the number of ways to choose, 4 members. 3 prefer smoking. Okay, and denominator is the number of ways to choose 4 members. So 150 choose 4, the ways to choose 4 members in a 150 member club, and the numerator is first you choose 3 out of the 30 that prefer no smoking, and then 1 out of the 120 that prefer smoking. That makes sense?
Yeah.
Do you have a question about it, or it make complete sense or some sense? Or
Yeah. I get it now. It's just that at first I had trouble understanding the sampling without replacement, like what it meant.
okay, so now for sampling with replacement. Okay, so let A be the same event as in part A. So little capital A is the same as the event, right? It's the same event, a random sampling of 4 members. The event of 3. Okay, so I'll just copy and paste it because wrong word. Okay, but now it's sampling with replacement. So now we're going to find the probability for sampling with replacement. So that means that, okay, so the probability is still N sub A over N. But now, so we want 150 members. Okay, so you want to choose 4 where you keep replacing person you choose. Okay, actually, let me do the numerator first. Okay, so you want to choose 3 out of 4 that prefer no smoking. So, okay, so each time you choose, oh, you know what? Sorry, wait, never get that. Okay, so if you, okay, so the probability of choosing someone who prefers no smoking is 0.20, right? And you want to choose 3 of them. And the probability of somebody who prefers smoking is 0.80, and you want to do that once. So you have 0.2 cubed times 0.8 to the first. But then you want to you want all the arrangements, right? So you have all the ways to arrange 3 out of the 4 choices. Choose 3 times that. This is the probability for one arrangement of like if you had S stands for smoking, N stands for not wanting for no smoking, right? And so this would be one possibility, right? Or you could have or NSNN, you could have NNSN, you could have NNNS, right? So there's 4 ways to arrange it. So you have 3 that prefer no smoking, 1 prefer smoking. So that's the same as 4 choose 3. 4 choose 3 is 4. And so for each of these orderings, the probability would be 0.2 cubed for not smoking and 0.8 to the first. So each of these has that probability. And so you would multiply it by 4 to get the sum of those 4 probabilities, or 4 choose 3 times that. Does that make sense? So it does? Okay, so that's with sampling and then without sampling. Oh, and then part C is compare the 2 answers. Okay, so okay, so you compute these and you compare the values. That's not hard to do. Okay, so I don't want to go into that. Okay, you get different values. Okay, so any other questions about the homework? Okay, so that's good. Okay, we have a lot of things to do, so keep going. But good question. Thank you for asking. Okay, so we last class we finished chapter 4 and we are now at chapter 5. And so let's start with chapter 5. So chapter 5 is about continuous random variables and probability density functions. Okay, so 5.1 is an introduction to this topic. And so when the set of possible values of a random phenomenon is of a continuous extent, real numbers, extent of real numbers, or is the real numbers. The value of the random variable, sorry, the value of the random phenomenon is a continuous random. Okay, so okay, so when the set of possible values of a random phenomenon is of a continuous extent, is a continuous extent of the real numbers, the value of the phenomenon is a continuous random variable. Okay, 5.2, probability density functions. Right, so like if a real value has real values, is real valued, then it's a continuous random variable, something like that. Okay, so the probability function f of x is equal to p of x equals little x. Okay, plays an important role in a discrete random variable. Okay, so let's say we shoot an arrow at a target, and f of x is equal to the probability. Capital X is equal to that probability, and which is equal to the probability that the arrow is little x inches from the center to the nearest. And so for part A, I'm going to say inch. Okay, so what we're doing is this: you have a target for a bow and arrow, right? And you shoot it, and so where the arrow hits the dartboard, you would measure its distance from the center, right? We're just going to take that distance where it hits the target from the center. We're going to round it to the nearest inch, right? So it's either have to be a larger amount or a smaller amount, depending on where you hit the target. Okay. If it's exactly in the middle, then I guess you just round up. Okay. So if it's 1.5 inches away, you just round it to 2. Okay. So we're always getting an integer inch, a certain number of inches, 1 inch, 2 inches, 0 inches, right? If it's 1/4 of an inch away from the center, then we round down to 0. Okay. Okay. So, so let's say you have that situation. So on the whiteboard, I'm just going to say, so for part A, we're talking about rounding to the nearest inch, right? And so let's say you draw the probability histogram for this situation. So a probability histogram is what you might think is a bar chart because it has bars on it, right? But we had an example of a probability histogram in another lesson. And so, you know, you have values, and then you have a rectangle centered at that value, and its height it tells you the value there, right? So, okay, so we have this picture, and it keeps going. Okay, so here's 8, and so at 8, there's another rectangle. Okay, good. And 9. It's another rectangle, and then at 10, there's nothing. So there are no hits to the nearest 10 inches. Okay, so this probability histogram is just describing, and the height of the bar is saying how many times. So you're like empirically, oh no, I'm sorry, the height is the probability, right? So it's telling you the probability, it's 1 inch, 0 inches, 2 inches, 3 inches, and so forth. So these heights are all less than 1. Now, for B, you could talk about, instead of rounding to the nearest inch, you could round to the nearest half inch. Okay. And so you'd have another probability histogram for the nearest half inch. Okay. And so you would draw the histogram. There'd be a corresponding histogram for half an inch. Okay. But then C, you could talk about the limit histogram. So you could talk about the limit of the probability histogram. So as you keep considering smaller and smaller units, sorry, limit of the probability histogram. So as you consider smaller and smaller values, eventually, so these are the original markings of it. Okay, but so eventually, instead of having rectangles, instead you have a continuous curve, right? But to match with what I wrote earlier, it's 0 at 10, right? Okay, so so now you have, so this is the limit of the probability histogram. So while before you had rectangles, these rectangles become smaller and smaller, but they approximate the height, of this final curve, and that's when you take the limit. So that's when you take these widths, these bases, these widths of these rectangles to be infinitesimally small. Okay, so you get a limit one. And so this curve in C is called the probability density curve of a continuous random variable. Okay, so the PDF, your probability density function, the function that tells you the probability of your random variable for a continuous random variable, looks something like this. Okay, it's the limit of the PDFs of discrete random variables, right? So there would be a discrete random variable for part A, there would be a discrete random variable for part B. So as you keep rounding to smaller and smaller units, right? Inch, half inch, quarter inch, eighth inch, 16th inch. Each of those random variables would be discrete random variables. There'd be finitely many values you'd be considering, right? The numbers would be getting larger and larger possible values, but it'd still be finite. If you take the limit, you now have infinitely many possible values, but your random variable is now a continuous random variable, and your probability density function is now a continuous function like this. Okay, so that's the idea of how you get a continuous random variable. Okay, so you have A, B, inch, and then C is the limit of probability histogram. Okay, so C whiteboard. Okay, so curve in part C is called the probability density curve of the random variable capital X, and is the limit of the histograms of the corresponding discrete random variables. Okay, so that's what I was just saying. Okay, so the function defined by this curve is called the probability density function of capital X, where capital X is a continuous random variable. Okay. So the probability that X is somewhere between A and B inclusive is equal to the definite integral from A to B of this PDF function. Okay. And the probability that X is at most a particular value, is equal to the probability that X is at most little x. Like this. So probably that negative infinity is less than X, less or equal to little x. And that's equal to the integral from negative infinity to little x of f of x dx. So this second equation is very essentially the same as the first one. It's just that the lower bound, instead of being a finite number, is negative infinity. Okay, see, this probability is from a to b, this probability is from negative infinity to x. And so instead of the lower bound being a to b, it's now negative infinity to x. And I'm actually going to change, instead of writing x here, I'm just going to put a dummy variable t. It's still x, but a dummy variable is just something, another, because we have x here already. So I have to use a different letter. Okay. Example 5.1. So consider the experiment of selecting a number from the interval 2, 4. Assume if subintervals I1 and I2 of that interval 2, 4 are equal in length. The probability of the number being in either interval is the same. Let capital X be the number selected. Then little f of x, the PDF for this function, is going to equal 1/2 for x values between 2 and 4 and 0 elsewhere. Okay, so you have an interval from 2 to 4, and any subinterval 2, 4, any two subintervals of 2, 4 with the same length have the same probability of the number, excuse me, of the number being in that subinterval. So let's go to the whiteboard. Okay, so you have an interval from 2 to 4. That's your space. And if you take a subinterval, let's say here, and another subinterval here, and let's say they have the same length. Okay, same length. Right, then the odds of x being in either subinterval is the same. Okay, the probability of either of okay, so the probability of x being in either interval is the same. Okay, that's the assumption. Okay, so the conclusion is just that the probability is just going to be that the probability of any subinterval of the same length is the same. And so the only way this can happen is if our f of x function was uniformly of value 1/2 everywhere on the subinterval. Okay, so the height is then 1/2. So the entire space is of length 2. From 2 to 4, the length is 2. But if the height of this function is 1/2, 2 times 1/2 is 1, right? So the area, the total area here is 1. Okay, so if the height is 1/2, then the total area is 1. 2 times 1/2 is 1. And if you take any subinterval, right? If you take any subinterval and you compute the probability, right, of let's call this set A, right? If I want the probability of something being in that set A, then it would just be equal to the integral from here's little a, here's little b. It'd be just be the integral from a to b of this f of x function. And so if you integrate this, then you get the integral from a to b. Now I'm not using colors anymore. A of 1/2 dx. Okay, so that's how you would compute the probability of a set. And so it doesn't, if you can tell that if you take any length interval that's the same, you'd be integrating over 1/2 from a to b, where b minus a is the same, right? So this is equal to b minus a times 1/2, right? That's the value of that definite integral. And so if you take any two intervals of the same length, then the difference of the right endpoint minus the endpoint, b minus a, is the same. And so the probability is the same. And so that matches perfectly with this assumption right here, right? This shows that. Same way, your PDF here is going to be the value 1/2 if x is between 2 and 4 and 0 everywhere else. And so this PDF function is then 0 here and 0 there. So it's 0 outside of this interval from 2 to 4, and it's 1/2 in it. And this assumption works with this choice. You can see that when you integrate over this PDF to find the probability, you always get b minus a times 1/2 for that. Okay, so it's 1/2 for x is between 2 and 4 and 0 everywhere else. And because it's a continuous random variable, it actually doesn't matter what happens at any one particular point. If you integrate, if you integrate over this function f and you change the value at x equals 2 or x equals 4, right? Instead of it being a height 1/2, you could change it to 0, meaning that this point here, I've chosen the point here to be 0 and this to be an open. So this is not 1 here, but it is 0 here. But it doesn't matter because integrating the value at one point doesn't change the value of an integral at just one point. You would need the values over an interval to be different to change the values of integrals. Okay, so that's your PDF right there. So this is example 5. So we get this PDF from this assumption that subintervals I1, I2 are equal in length, and the probability is the same of a number being selected in either one. Okay, so now example definition 5.1. A real valued function, capital X, defined on a sample space, capital S, with probability set function, capital P, is a continuous random variable, provided that there is an integrable function f such that probability of x being at most little x is equal to the integral. Is equal to the integral from -∞ x of little f of t dt, where t is the dominant variable. And this is for any x, any finite x. Okay, means any finite x. Saying it's between -∞ and infinity, strictly between -∞ and infinity means it's any finite, means for finite x. Okay, so so this is the definition of a continuous random variable. It's a random variable in which there exists an integrable function f, in which you have this happen, that the probability of x, capital X, being at most a certain value can be expressed as this integral. So Kashan, what do you mean by it has to satisfy the integral? Okay, see, I said, and you asked something in the chat. I didn't understand the question. Okay, so the function f is a probability density function of the random variable capital X. Okay, so we call this function little f here a probability density function of the random variable x. Okay, so this is 5.4. Is that right? 5. Oh, okay. Okay, so this was 5.3 continuous and variables. Okay, so 5.4 is finding probabilities for continuous random variables. Okay, so these are rules for finding probabilities for continuous random variables. 1, the probability of x equal to little x is 0 for negative infinity less than x less than infinity. 2, the probability that x is at most little x is equal to the probability that x is strictly less than little x. Okay, or I'm going to put it this way, strictly less here, less or equal to here. Okay, so these two probabilities are the same. You can remove a point here and it doesn't change the probability. And this probability is already, as we defined it, as we already talked about, this is the integral from negative infinity to little x of f of t dt. And so this is for any finite x. So that's the third rule. I mean, that's the second rule. The third rule is that the probability of a between x between a and b inclusive is equal to the probabilities where you keep or don't keep any of the endpoints of that subinterval. So you can remove only the point b, that's the same. You can remove only the point a, and it's the same. You can remove both points, and it's the same. And so all four of those probabilities are equal, and they are all equal to the integral from a to b of f of t dt, where little f is the probability density function for capital. Okay, and this is for a strictly less than b, where the a is here, the a and b in these intervals. A is strictly less than b. Okay, so observe that the probability of a strictly less than x less than or equal to b is equal to the probability that x is less than or equal to b minus the probability that x is less than or equal to a. Okay, so I think I showed this there was another situation where this came up, I think, for discrete. So what's happening is that the probability that a is less than x less than or equal to b is equal to the probability of x at most b minus the probability of x at most a. Okay, so if you have a line, right, and so you have values from you have a here and you have b here, right? So so the probability that x is at most b would be the probability of this space, right? So this would be the probability of this space would be the green line. Now, if you subtract from it the probability of a, x being at most little a, you'd maybe subtract these values, the probability of this space, right? And so if you subtract the chances of it being in the green space minus the chances of being in the purple space, what you're left with is the chances of it being in the blue space, where it doesn't include the left endpoint, but does include the right endpoint, right? We have the right and green endpoint, removed the A point because we subtracted the purple probability. So we're left with this integral, this space of blue values. That's this space. It's the probability of A strictly less than capital X less than or equal to B. Okay, and so the probability of this blue region is equal to the probability of the green region minus the probability of the purple region. So this probability equals this probability minus that. Okay. Okay, so that's how we get this equation. Okay. So that is drawn, that is illustrated on the whiteboard. Okay, so let's keep going now. Okay, so then this first probability, the probability that capital X is at most B, is the integral from negative infinity to B of f of t dt. Okay. But now we're going to subtract the other probability, which is from negative infinity to A of f of t dt. And so then that's equal to, okay, so if you're integrating from negative infinity to B and you subtract the integral from negative infinity to A, you're left with the integral from A to B of f of t dt. But from calculus, right? This is from calculus. Remember, in calculus, that if you have the integral from A to C of f of t dt, and you add the integral from C to B of f of t dt, that's equal to the integral from A to B of f of t dt. Okay, and so you can extrapolate from that. You can deduce from that that the you could also take this integral and say it's equal to this integral minus that integral. Okay, so that's kind of what's happening here. So then you just choose the appropriate letters, and so then you would have that the integral from A to B would equal to this expression, where you're allowing infinity. So here the A would be negative infinity. Here B would still be B, but C would be A. So you replace C with A and A with negative infinity, and you would get this equation. Okay, and so that would imply this. What's going on? Okay, screen. Okay, this would be that would imply that using different values for letters. Okay, so not using A in the same way, just changing the letters around. Okay, good. Okay, so then, okay, so we have that the probability from A to B is equal to this depth integral, and so we get that from this. Okay, so given this probability defined in this way, we can get that the probability of this integral is equal to that depth integral. Okay, so with just this assumption, we get the result from earlier. Okay, so also observe that if you take the limit as C approaches 0 of the probability that X minus C is strictly less than capital X, strictly less than X, less than or equal to, this is equal to the limit as c approaches 0 of the integral from x minus c to c of f of t dt. Okay, so if you take the limit as c approaches 0 of this probability, the limit as c approaches 0, then the thing you're subtracting is going to 0. So that means that's really the probability of x equals c. Okay, but so what this implies is that, well, the left-hand side of that equality is the probability capital X equals little x, right? This limit is just the probability of x equaling little x. The right side, if c goes to 0, then that means that you're taking the integral x minus c to x. Sorry, if you're taking this probability, it's from x minus c to x, so it's x minus c to x, and you're taking the limit of that. So if you're taking the limit of c approaches 0, the lower integration limit is going to x. And so if you integrate from x to x, that's 0. So this implies that probably x equals little x is 0. Okay, so our conclusion there is that the probability of x equaling any fixed value is 0. So the only way you get a positive probability is if you consider more than one point. But it's going to have to be like an interval of points, not just 2 points. It's not enough. But if you take the probability of any one particular point, it must be 0. That's what that says. Okay, so example 5.2 is let capital X be a continuous random variable with probability density function f of x, which is equal to 2x for 0 less than x less than 1 and 0 elsewhere. Find the probability of x at most 0.4, the probability of x greater than 0.2, probability of 0.2 less than x less than 0.4, probability of x equaling 0.5, and the probability that x is strictly less than 0.4. Okay, so we're going to find each of those probabilities with this continuous random, our continuous random variable with this PDF. So the probability that x is at most 0.4 is then equal to the integral from negative infinity to 0.4 of little f of t dt. And that's equal to the integral from negative infinity to 0.4 of that PDF f of x. Okay, but since it's 0 for x less than 0, we don't have to start at 0. We can start at, we could start at 0 to 0.4, right? And the PDF is 2x. Okay, and for this time, I'm not going to do this every time, but for this time, if I were to then, I'm really breaking apart this one integral into two integrals, from negative infinity to 0, and then from 0 to 0.4. But here, the value is 0, right? The f from negative infinity to 0, it's about f of x is 0, integrand is 0. But from then 0 to 0.4, PDF is 2x. So I break apart the interval from negative infinity to 0.4 to negative infinity to 0 and 0 to 0.4. In the first interval, the f of x is 0, and on the second interval, the value is 2x. And so the first integral is 0, and then plus, well, the second integral is x squared evaluated from 0 to 0.4. And so that's equal to is 0.4 squared minus 0 squared. Okay, and so that's equal to 0.16. So the probability that x is at most 0.4 is 0.16. The probability that x is greater than 0.2 is equal to the probability that 0.2 is less than x, less than infinity. Okay, and so that's equal to the integral from 0.2 to infinity of that PDF, right? Of f of t dt. But because this PDF is 0 everywhere outside of from 0 to 1, we should break up apart this integral from 0.2 to 1. And then the rest of the integral plus the integral from 1 to infinity of that PDF. Well, the first PDF, so the first integral, f of t, is to use x. We don't need a dummy variable for this example. So in the first interval from 0.2 to 1, the value of the function is f of x from 0.2 to 1 is 2x there. So you have a 2x there. From 1 to infinity, it's 0, right? So f of x is 0 from 1 to infinity. And so then that's equal to, well, the first integral is x squared evaluated from 0.2 to 1. Okay, let me maybe write that bracket. Let me try doing it this. Let me do it this way. You have x squared evaluate from 0.2 to 1. Maybe it's a little clearer that way. Okay, and then plus the other one's 0, right? If you integrate 0, you get 0. Okay, so this is equal to you have x squared evaluated at 1. So you have 1 squared minus 0.2 squared. And so that's equal to 1 minus 0.04. And so that's equal to 0.96. And so the probability x is greater than 0.2 is equal to 0.96. Okay, so I'm evaluating it directly. You could have also said the probability x is greater than 0.2 is 1 minus the probability x is less or equal to 0.2. But I don't think that would be less work. Okay. The probability that 0.2 is strictly less than x, strictly less than 0.4, is equal to, now you can also, once you understand this, right, you can just say this is from 0.2 to 0.4 of f of x dx, little f of x dx. Okay, because we have the result from earlier. Right? We have the result that the probability of this interval is equal to that definite integral. Right, the probability of this is equal to that integral. Right? So this is from the fact that we have this probability is equal to this definite integral. Okay, and so now this is equal to, so from 0.2 to 0.4, that lives entirely in the unit interval from 0 to 1. And so f of x there is 2x. So I can substitute this f of x here for 2x. So now f of x in that subinterval is 2x. So we just want to integrate that. Well, an antiderivative of 2x is x squared, and you evaluate it from 0.2 to 0.4 by the fundamental theorem of calculus. And so this is equal to 0.4 squared minus 0.2 squared. And this is equal to, you have 0.16 minus 0.04. This is equal to 0.12. Okay, so this probably this interval is equal to 0.12. And this is from earlier. Okay, the probability that x is equal to 0.5 is 0. Right? This is from the earlier fact, the probability of x equaling any fixed value has to equal 0. So we know that this has to be 0 because I just plug in little x equal to 0.5. And that tells me that that probability is 0. And if the probability that x is strictly less than 0.4, well, that's equal to, I can put the in-between step here for now. Normally, you don't have to write that. It's equal to probably x is less or equal to 0.4, and that's equal to the integral from negative infinity to 0.4 of f of x dx. Right, and then this is equal to the integral. So you split up into two integrals, one of them is 0, right? So for shortcut, you write 0 to 0.4, and PDF is 2x there, so you would have that. And so an antiderivative of 2x is x squared, and you evaluate it from 0 to 0.4. So this is equal to 0.4 squared minus 0 squared. And so this is equal to 0.16 minus 0, which equals 0.16. Okay, so a shorter way to write the last one is this. So if you could just write probably x is strictly less than 4 is equal to the integral from 0 to 4 of 2x dx. Now, so it's for this example, right? It's this example, right? In other examples, it's not that. But because we know the PDF is 0 when x is less or equal to 0, we can start at 0 and then end at 0.4. And so then this is equal to, the rest would be the same, x squared evaluated from 0 to 0.4. So that's equal to 0.4 squared. That's fine. I'm just so that there's no confusion here. Minus 0 squared, and that's equal to 0.16. Okay, so you don't have to write all those steps there. I'm doing it just to break it down step by step for you so it makes sense. You can write it like this, and that's absolutely right. Okay. Okay, so next example is example 5.3. So suppose in a region, the daily rainfall in inches is a continuous random variable, capital X, with probability density function, little f of x, given by the following function. Okay, so f of x is equal to following. Good. So 3/4 times 2x minus x squared. This is for 0 less than x less than 2, and 0 elsewhere. Okay, so we're supposing in a region the daily rainfall in inches is a continuous random variable with this probability density function, right? PDF is short for probability density function. So find the probability that on a given day in this region, the rainfall is each of the following. So for A, not more than 1 inch. Okay, so here, capital X is the amount of rainfall. So what we want is not more than 1 inch, right? We want the probability that it is not more than 1 inch. Okay, so we want the probability that it's not true that X is greater than 1, which means it's equal to the probability X is less or equal to 1. Okay, and so this is equal to just the definite integral from negative infinity to 1 of this PDF function. Okay, and so now you plug in that PDF function, which is this. Well, okay, so since it's only for between 0 and 2, then that means that you only need to look in the interval from 0 to 2. And so you only need to look here from 0 to 1 because we stop at 1. So this is equal to the integral of that function from 0 to 1 with this integrand from 0 to 1. Okay, and so now you integrate that and then you get your final answer. So you have 3/4 as a constant that you move outside of it, and then the antiderivative is x squared minus 1/3 x cubed. And so you want to evaluate it from the lower limit 0 to the upper limit 1. And so now this is just calculating an integral. And so now we have, okay, so now we have the value at 1, which is 1 squared. 1 squared minus 1/3 times 1 cubed minus the value at 0, which is 0 squared minus 1/3 0 cubed. Okay, so we're just evaluating the integral, and I'm just putting in an extra step so it makes sense, right? I'm integrating this. I moved the constant outside the integral, and I found an antiderivative of 2x minus x squared, which is x squared minus 1/3 x cubed, and I evaluated from the lower limit to the upper limit. So I evaluated an antiderivative of the integrand from 0 to 1 using the fundamental theorem of calculus. They're equal. It's a 3/4 times it. So 3/4 times this, where I plug in 1 into this expression, which is 1 squared minus 1/3 1 cubed, and that goes there. Then I plug in 0 into this expression, and I get 0 squared minus 1/3 0 cubed. So I did first expression minus that expression. That's the value that represents this quantity in brackets represents this quantity in brackets. Okay, so that's equal to, so you have 3/4 times the bracket quantity, which is 1 minus 1/3 minus 0. This is equal to 3/4 times 1 minus 1/3 minus 0 is 2/3. So 3/4 times 2/3, the 3's cancel, 2/4 is 1/2. So the value is 1/2. So the probability that the rainfall is not more than 1 inch is 1/2. As a decimal, it's 0.5. Okay, so you also have the probability. So for part B, we're just going to write the probability here. We want to find the probability, find the probability that the rainfall is greater than 1.5 inches. So you want X, the amount of rainfall, to be greater than 1.5. So that's equal to the integral. So it's from 1.5 to infinity, but because our PDF is only non-zero from 0 to 2, we're going to go from 1.5 to 2. The rest of it doesn't matter. That's the PDF there. So we have that PDF. And so now you evaluate this definite integral from 1.5 to 2. Well, we already evaluated an antiderivative of this expression and got this, where the lower and upper limits were 0, 1. So now I just want to change the lower upper limits to 1.5 to 2. Okay, so this is an expression for an antiderivative of the integrand. Now I'm valuing new limits because I have new limits of integration. Instead of from 0 to 1, it's from 1.5 to 2. Okay, and so this is equal to 3/4 times. So one thing minus the other thing. The first thing is when you plug in 2. You get 2 squared minus 1/3, 2 cubed. You get 2 squared minus 1/3 times 2 cubed. And the other expression, you plug in 1.5. So you get 1.5 squared minus 1/3 times 1.5 cubed. I want to write 3/2, but I didn't want people to lose me here. So I plugged in the same number I wrote down. So I put 1.5 here. So then this is equal to 3/4 times. So you have the first thing minus the second thing. Okay, and so 2 squared minus 1/3, 2 cubed is 4 minus 8/3. So 4 minus 8/3 is 12/3 minus 8/3, which is 4/3. There's a 4/3 there. Okay, and then you subtract the other expression, which is this expression. You have 3/2 squared, which is 9/4. 9/4 minus 1/3, 3/2 cubed. 3/2 cubed is 27/8 times 1/3 is 27/24. So the expression we have here is 27/24. And we're subtracting from that the first thing, which is 3/2 squared, which is 9/4. Okay, so this is the thing. Okay, so then this, I'll just rewrite it. 9/4 minus 27/24. Computer doesn't want me to do that. Okay, so then to subtract the two things, this is equal to 3/4 times. So you have 4/3 minus, I guess maybe a multiple distribute. So you have 3/4 times 4/3 is 1 minus. So 3/4 times 9/4 is 27/16. You have 27/16. But then you have minus is a plus. So you have 3/4 times positive 27/24. And so then that's 8 in the denominator. So you have 27/32. This is however way you'd want to calculate this. So this is 32/32 minus 54/32 plus 27/32. I just wrote them, each of these three terms, using the denominator 32. Okay, and so if you calculate this, you get 5/32. And as a decimal, this is equal to 0.15625. I was just evaluating it as I have as a fraction and as a decimal. Okay, so part C, I'm going to find the probability of the amount of rainfall is between 0.5 and 1.5 inches. So that's the same as the probability that 0.5 is less than x, less than or equal to 1.5, right? I can add or remove points on the endpoints, right? So this is the probability that x. Actually, never mind. We don't have to prove that again. Okay, so it's between there and there. And so it's going to be whether I do or don't include endpoints doesn't matter. And so it's from 0.5 to 1.5. 0.5 to 1.5 will lies in that interval. And so the PDF there is this. There's the PDF. There's the PDF. And so you integrate that now. So we already have the integrand over here. We already have this. We just change the limits of integration. So we have 0.5 to 1.5. And so this is equal to 3/4 times. So if you plug in 3/2, Oh, okay. So then it was this value here. This is what it was for 1.5. Okay, so you have that thing. That was for 1.5. Okay. And then you subtract the value at 1/2. So at 1/2, you have 1/2 squared, which is 1/4. So you have 1/4 minus 1/24. Okay, so you get that whole thing. Then you calculate that and you get 0.6875. So for part D, you want to find the probability that it's equal to 1 inch. So the probability that our continuous random variable, the amount of rainfall, is exactly 1 inch is equal to 0, right? And E, we want to find the probability that the amount of rainfall is less than 1 inch. So the probability that X is strictly less than 1. Well, that's equal to the integral. So anything less than 0 doesn't matter because the values of F is 0. So we start at 0 and we end at 1. We end at 1. And our PDF is still the same. It's 3/4 times 2x minus x squared. And I'm happy because we're dealing with the number 1 here. So this won't be an annoying calculation like before. So now this is going to equal 3/4 times an antiderivative of 2x minus x squared is still x squared minus 1/3 x cubed. And we're evaluating it from 0 to 1. So this is equal to 3/4 times the first term minus the other term. The first term is plugging in a 1, so it's 1 squared minus 1/3 times 1 cubed. The other term is plugging in 0, so you get 0 squared minus 1/3 times 0 cubed. So this is equal to 3/4 times. So the first term is 1 squared minus 1/3, 1 squared. So that's 1 minus 1/3, which is 2/3. 2/3 minus 0. So 3/4 times 2/3 is 1/2. And so the value, probably it's less than 1 inch, is 1/2. Okay, so that's that entire. So now next, okay, so just okay. So next is example 5.5, which is on a third type of random variable. Okay, so let's consider this situation. So let's consider this situation. So the goal is to see that there are random variables that are neither discrete nor continuous. So neither. Okay. So toss a coin. If heads, the player gets 10 ounces of beer. Okay. If tails, the player presses a button and receives anywhere between 0 and 100, 0 and 10 ounces of beer. Let capital X be the amount of beer received by the player in the experiment. Explain why X is neither a discrete random variable nor a continuous random variable. Okay. All right. So, right. So, okay. So, I like the reaction because I'm talking to a blank screen for the last hour. So, okay. So you toss a coin. So if it's heads, you get 10 ounces of beer, right? And if it's tails, you press a button and receive anywhere between 0 and 10 ounces of beer. Okay, so X is the amount you get, right? So we want to show why X is not discrete nor continuous. Right. So first, let's think about something obvious, quote unquote. The set of possible values of capital X is the entire interval of real numbers from 0 to 10, right? Therefore, X is not a discrete random variable, right? The sample space, the set of possible values of X is neither finite nor countably infinite. So the set of possible values of capital X is not discrete, right? So the set of possible values X cannot be discrete because its set of values are all the real numbers from 0 to 10, right? So X is not, I'll call this obvious observation. So X is not a discrete random variable. Okay. But we want to say why it's not neither discrete nor continuous. So this is a little bit harder, but once you see it, it makes sense. The probability of heads is 1/2, right? Therefore, the probability of X equaling to 10 is greater than or equal to 1/2. Okay, so X is the amount of beer you get. If you flip heads, you get 10 ounces of beer, right? And there's a 1/2 chance. There's a 1/2 chance, right? That when you flip the coin, it's going to be heads. And every time it's heads, you get 10 ounces of beer. So the probability X is exactly 10 is at least 1/2. Now, when you flip tails, you get anywhere between 0 and 10. So there might be a chance that if you flip tails, you still get 10 ounces of beer. But regardless of what that chance is, you already have 50% chance odds by flipping it heads. So probably that X equals to 10 is at least 1/2. Okay. So the probability that X equals 10 exactly is not equal to 0, right? The probability is greater than or equal to 1/2, which means that it cannot be 0. 0 is not greater than 1/2. And so this contradicts one of the properties of a continuous random variable, right? For a continuous random variable, the probability of any fixed value has to be 0. And so since here it's non-zero, thus X cannot be a continuous random variable. So X is not a discrete random variable. It is also not a continuous random variable. Okay, so we still have an experiment and we have a random variable. It's just one that's neither a discrete random variable nor a continuous one. And so this is an example showing by construction how there are variables that are neither discrete nor continuous. Okay, so we'll stop here.
Okay.
But before you go, let me just think about the homework for a second.
I have a question.
Yeah.
So if X is continuous, right? So
Yeah.
So the probability of X equals 10 is equal to 0 if X is continuous.
That's if X is continuous, right?
Oh,
But here we show that the probability X equals 10 is not 0, because if a number is greater than or equal to 1/2, it can't be 0, right?
okay, yeah.
And so that means that the probability of X being a fixed value is non-zero. And so it has to be in order to be a continuous random variable, which means it's not continuous.
Okay, yeah.
All right, good. Okay, so you get it. Okay, good. Okay, so there's no homework for next class. So I'll see you on Thursday, and have a good night. Bye, everyone.
Very good.
Thank you, Professor. Good night.
You're welcome. Good night.